Welcome back to numerical methods. We're going to finish up our discussion on partial differentials equations today. So just as a reminder, last time we started partial differential equations, we talked about using the two-dimensional time independent finite difference, where we had, say, partial squared t, maybe partial squared x plus partial squared t partial y squared equals 0, and how we can implement this with having two boundary conditions. Then we also considered time-dependent equations, or really having only one boundary value problem, so say maybe dt dy squared, and then one initial value problem, d squared t dx. Oops, not squared, just partial t partial x equals some function. And so here we had two boundary conditions. Here we had one boundary condition and one initial condition, right? And so we sort of talked about the differences with that using a finite different approach. Today, we're going to talk about just jump in a little bit, talk about Robin's boundary conditions, then we'll talk about implicit methods, and then finally we'll talk about a finite volume approach to solving partial differential equations. So let's go through very quickly and talk about the different boundary conditions that we have. So far we've really talked about Dirichlet boundary conditions. So remember, in this case, if I have a set of nodes along my finite difference points, I can look, say to the left or to the right, and I have a fixed value. I don't know, maybe 5 or -7. And those are fixed. We then talked about Neumann boundary conditions, where we had dt dx is some value, right? So if I was looking in, say, this sort of same set of nodes, what we would do is we would make an additional node out here that's going to serve as the boundary condition, and then we have that imaginary node, and we say that the value of that imaginary node, say maybe ti plus 1, is equal to ti minus 1 times 2 plus whatever that function is. So let me just correct this really quick. So times 2 delta x plus whatever that function is. Okay, and then we could do the same thing, with that imaginary boundary condition over here. So notice how this function, we usually think about this as being 0, but this could be sort of any other set of number. We could also have now this Robin's boundary condition. In this case, we have our dependent variable over here. So if I draw out this same set, I still need to implement this imaginary node, but this time my formula is a little bit more complicated. So here, let's write things out. So we could say maybe dt partial x is some constant, I don't know, h over k times t minus tf. And in this case, this t, right? If I have a node here, right? Ti, I've got my t I plus 1, and then my node I minus 1. Now we need to start including this t. So this t is ti, right? So I can still take this derivative. So this is ti plus 1 minus ti minus 1 over 2 delta x equals h over k ti minus t, say f. And now I can rearrange it just like I did up here, but we have now an additional term, right? So we've got ti plus 1 is equal to ti minus 1 plus 2 delta x h over k ti minus tf. Okay. So just adding that extra complication, but it's the same idea as the Neumann boundary condition, but instead of having this much simpler form, we have to take into account that ti into there, and we can't just say, okay, it's the value here is there. So we could maybe have to add in an additional imaginary node into our system just to take this into account. But the ideas are going to be identical. Okay, so these are all of the boundary conditions that we're going to discuss for this class. So now let's move on to different methods for solving these types of problems. So we're going to go back to the types of problems where we had one boundary condition, so maybe t squared partial x squared plus partial t partial time equals some function, right? And previously, we had talked about solving this initial and boundary condition problem using an explicit method, where we solve for that space dimension, so the boundary value problem on these 3 points, and then we solve for the initial value problem, B, C, then we solve for this initial value problem only on these 2 grid points. So if we had just set this equal to, I don't know, 5, remember we would say that, or maybe let's set this equal to 0 just to be really easy. We had said that in the explicit method, we had t L plus 1 at point I would be t at point L, so that time point, at point I, so this point plus my time step times whatever that second derivative was. So whatever the whatever is happening down here, we could take that as L TL I minus 1 minus 2 TL I plus TI plus 1 minus 1 all over delta x squared, right? So we're using these 3 points down here and then this point up here. And so when we do this out, we end up having to take relatively small time steps in the time direction relative to the points in the space direction, just so that we, because we're using less information, and so that we don't have this oscillatory behavior. Now, if you remember back to when we were talking about just initial value problems, remember that we had both explicit and implicit methods. And the implicit methods, which had to be solved iteratively, ended up giving us better solutions because we know more information about the system. And so we can take that same idea and apply it to these partial differential equations, where we're going to solve, we're still going to use the previous point in time, but now we're going to solve my spatial component up top. Right? So we're going to rearrange this, and then we're going to end up having to do this in an iterative fashion. But we should end up with a better solution to the problem. So let's sort of continue on with this idea. We're going to take a heat transfer equation. We have some k partial squared t partial x squared times partial t squared. And we're going to now take our partial derivative steps. So just our differential, our finite difference steps. So just like before in the explicit method, I can write out my partial squared t partial x squared. But notice now I'm using the time step that I'm solving for. Remember, of course, that this is time, and this represents space. So if I'm interested in solving for the next time step, I'm at time L plus 1. So that's that next time step. And I'm going to take that finite difference over space on that next time step. So, right, so if I already have this row, this is solved. This is maybe L. This is what I'm solving for, so L plus 1. I'm going to look at the nodes on this L plus 1 row. Okay, everything else though is the same. I'm still using a central finite difference for my second derivative. Okay, and for my time step, we can write this out. So partial t is going to be essentially the same as it was before. It's the, I can only take a backwards derivative because I don't know what forwards is. So we can just say that t at L plus 1 at point I is delta t is t of I L plus 1 ti minus ti at point L. So now I'm looking between these 2 points over some time. So I can take these two equations and I can put them into that top equation, and I end up with this. The nice thing here is that we end up with this form. Okay, so let's pull this forward. I'm going to put these equations essentially same set, just all written out. So now it's time to rearrange this into some form that we can use to solve a problem. So remember, before we tried to isolate this ti plus 1. We're going to do this sort of again. So we can rearrange this problem to isolate this ti. So I'm going to move delta t over. I'm going to move t li over. Okay, so we end up with ti of L plus 1 is equal to TIL plus delta t times k times over delta x squared times all this stuff up top. So this is ti plus 1 L plus 1 minus 2 ti L plus 1 plus ti minus 1 L plus 1. Okay, so in this case, I could go a little bit farther and pull this function over to this other side to set up a linear algebraic solution, because we've got this linear case. So let's go ahead and do that. But remember, if this is nonlinear, or in other words, if there was an additional t term in this equation that's nonlinear, I don't know, natural log t, whatever, I would not necessarily be able to just pull this out. But in this case, we can. So let's do that. So we're going to move that negative 2t over. So we end up with ti L plus 1 plus delta t dot k over delta x squared times 2 ti L plus 1. And so that equals ti L plus 1 times 1 plus 2 delta t, 2 delta t k over delta x squared equals all of that. And then I'm going to just write the final solution out. Oops. I'm going to write the final solution out so that we have it. We have t I l plus 1 is equal to t I l plus delta t k delta x squared times t I plus 1 l plus 1 plus t I minus 1 l plus 1 over 1 plus 2 delta t k over delta x squared, right? So this now gives us an equation that we can work with. Okay, so this is that solution for each of those points. Notice, of course, that we have these L plus 1 terms on the right-hand side. So I can't just punch in numbers because these are unknowns. So this means we need to solve this problem simultaneously, right? So we have to put together all these simultaneous equations. And let's do this in two terms. So we're going to do this via linear algebra. So putting linear algebraic terms together, and then we'll do it for Gauss-Seidel. Okay, so let's put this into action. Let's assume that we have a 4-meter rod with 3 nodes. So let's say here to here, we're going to have 1, 2, 3 nodes. On the left side, we'll have a temperature of 300. On the right side, we'll have a temperature of 500. And we're going to solve this given that k equals 2, and we'll take a time step of 0.1. So since we have 3 nodes, and we have 4 meters, this is 1 meter, 1 meter, 1 meter, 1 meter. So delta x equals 1. Okay, so let's look at the first node. So T1 at maybe step 1 is going to be the initial condition. So maybe we set all of these to 0 initially, or how about this? We'll set them equal to 100, 200, 300, just to give us some differentiation. So at this point, our initial condition is 100 plus delta tk. So that's delta t is 0.1, k is 2 over delta x, which is 1 squared, times our ti minus 1. Okay, so that's looking over at the boundary condition. So that's 300 plus plus this point to the right. So we don't know what that is right now, so we have to leave that in there. So that's T2 at time, at time 0.1, 0.1, all over 1 plus 2 times 0.1 times k, which is 2 times 1 squared. Okay, so we have all of this information, but now we want to put this into a linear algebra solution. So we can rearrange this. So we end up with 1 plus 1.4, because that's what this is on the bottom, times t1 times 0.1. Then I move over some of these points. So here we have minus, because I have to move over that 2t. So we get a minus term over there. Minus 0.2 times t2 times 0.1. And then everything else ends up on the right-hand side. I'm going to leave some space, and then we have everything else over here. So this is 100 plus 0.2 times 300. Okay, so now we're ready to do the second one. It's going to have relatively the same form. We're not going to write necessarily all of it out. We can go maybe a little bit faster. So here we have 0.2 at 0.1 is equal to, okay, I look, my previous step was 200 plus 0.1 times 2 over 1 times the point to my left. Well, that's t1 at 0.1. The point to my, because it's here, I look the point to my right. I also don't know that point, so that's 0.3 at 0.1, all over 1 plus 2 times 0.1 times 2 over 1 squared. Okay, so now I can go ahead and write this out. So this gives me 1.4 times t2 0.1. Now I need to pull over the t1 and the t3, right? So here we have minus 0.2 t1 at 0.1 minus 0.2 t3 at times 0.1. And then that equals everything that's left over. So that's, in this case, just 200, or the original temperature. Okay, so now let's go on to the next slide, and we can do that final, maybe we can fit it in over here. I'm gonna maybe, we'll go on to the next slide and do this again. Okay, so now we're ready for T3, so T3 at 0.1, and that was, what do we say, the original temperature there was, say, 300 plus 0.1 times 2 over 1. In this case, it's T2 at my current time step plus T4 at my current time step, all over 1 plus 2 times delta T, 0.1 times K2 over 0.1. Okay, so now we're going to end up with a similar equation. We have 1.4 T3 0.1. Oops, that should just be a 1. There we go. 1.4 T3 equals, now we need to pull over these two. So I don't need to pull over T4 because that's a known, but I do need to pull over T2. So we have minus 0.2 T2 at 0.1 equals now everything that's left over. So that's 300 300 plus 0.1 at 0.2 times T4, which is 500. All right, so now we have this equation, and we can start rewriting this whole set as a matrix. So remember, we want to get these all well aligned. So here's our T1 at 0.1, T2 at 0.2, sorry, 0.1, T3 at 0.1, and then this equals everything that we sort of had on those previous two slides, which was 300 plus 0.2 times 500. If you remember back for T2, it was just 200, and then for 0.1, it was, let's go back and look, 100 plus 0.2 times 300. So 100 plus 0.2 times 300. Okay, and so then we just need to fill in the front matrix. There's no T1s for this first case, so we put in a 0. We have a negative 0.2 for T2, and then a 1.4 for T3. Now we can go back, look and see what we had for T2. That was 0.1 times T2, and then negative 0.2s for the other two cases. So negative 0.2 for T1, 1.4 for T2, negative 0.2 for T3. And then we're going to see the same thing for T1. So if you remember, we had 0.1 times T1, negative 0.2 times T2, and 0 for T3. We have a tridiagonal matrix. We can use one of our methods for solving this to get all of our new points. Okay, so once we have this all set up, right, these new T1s are going to become, are going to move over here and going to move over here and become this first part. So this 100, 200, and 300 will be substituted by this T1, T2, and T3 when I go ahead to look at times 0.2. Okay, so we can just update this piece by piece. All right. So we've already sort of set this out a little bit for Gauss-Seidel. We can just rewrite those equations. What did we have? T1 at 0.1 is 100 plus 0.2 times T2 0.1 plus 300 all over 1.4. And then we can write this out for T2 was 200 plus 0.2, T3 0.1 plus T1 0.1 over 1.4, and then T3 0.1 equals 300 plus 0.2 T2 at 0.1 plus T4, which is 500 all over 1.4. So in this case, we would go in and go ahead and do Gauss-Seidel. So what we're really saying is, as I move from one time, so t equals 0 to t equals 0.1, before we just went through and we looked at each individual point and we moved it forward in time, right? This was the explicit method. Now with the implicit method using Gauss-Seidel, I need to do this iteratively. So I need to go from, loop through these different points, or I need to use something like a linear algebraic solution, okay, which will do this all at the same time. Okay, good. So the implicit method should give us fewer errors, but is going to take an iterative approach. Okay, let's move on to a slightly more complicated method. Let's look at a more complex problem. In this, previously when we were talking about having initial boundary conditions and initial value conditions, we had only one initial condition and only one boundary condition. But in reality, we can have something more complex where I have two boundary conditions. This is going to make our life a little bit more challenging because we need to take our finite differences in all of these different directions. So the way that we can solve this is using the ADI method. This is going to combine the explicit method and the implicit method together, as well as sort of taking half steps. So what we're going to do is we're going to break our problem down into two. We're going to go from time TL, so this initial condition, to time TL plus 1. But we're going to do it in two steps. So we're going to take a half step here and then a second half step. And why we're going to do this in half steps is because we're going to mix and match our implicit and explicit methods so that we can evenly treat our problems. So what we're going to do is we're going to use the explicit method in, say, the y direction first. So I'm going to go from this line, so using this information on these 3 points upwards to solve for this to this point, which is halfway to the point that I'm interested in. But I'm going to solve implicitly in the x direction. So this way I'm bringing information from both the x and the y direction together at the same time. So this one's explicit. This one is implicit. Now, if I were to do this again, in the next half step, I would have an uneven treatment of my x direction and my y direction, right? Because I would have that implicit method is more accurate. So I would have treated the y's better than the x's. So now we're going to flip it. In the second half step, I'm going to go explicit in the x. So I'm going to look backwards at these x points and do implicit in the y direction. So these points are now implicitly solved for. Okay, so this is the idea. I'm just going to go ahead and show you sort of the equations rather than do an implementation, because you can start seeing that these implementing these methods starts getting quite time consuming to write everything out and do. The ideas are going to be the same for how we solve the implicit part to what we just talked about. And that nice explicit part is just going to give us constants. Okay, so let's go ahead and look at this. So what we've done is I've written out that equation. Remember, it was partial t partial time equals k partial squared time partial x squared plus partial squared time partial y squared. And I've written it out in our finite difference approach. So here we have the time piece, and now I can break up my x's and my y's. So first, my first step is to go explicit in the y's. So notice here, here's my explicit. So notice here that my i's, I plus 1, ij, they're all at the same j, and they're all at my previous time step. So they're all at L, right? So I've got TL plus 1 and TL. Notice these are all at L. And these are all at moving only in the x direction. Now I'm going to bring in my implicit part in the y direction. So note here, my y direction is changing, so I is the same, but I have j plus 1, j, and j minus 1. But my time step is all L plus 1/2. Okay, so the x matches here, and the y's match here. So this explicit part, when I solve this out, this should just be a number, because I know all of my previous steps. So this should give me, that explicit part should give me a solid number. the implicit part needs to be solved for iteratively or linear algebraically. So we can do either Gauss-Seidel or linear algebra to solve for that half step. And I can pull out this ti plus 1, plus 1/2 by moving these two terms over to the other side. So once I solve for all of those points in the y direction, implicitly, I can move on to my second half step. Now this time, I'm going to go from ti plus 1/2, so what was solved here, to ti plus 1. And now I'm going to flip my set. So the x set is going to become implicit, and my y's are going to be explicit. Okay, so notice for the y sets, now it's L plus 1/2, L plus 1/2, L plus 1/2. So these are all coming down from that previous step. So this term is just a number, right? Because I know all of that information because I just solved for it. These pieces, we don't know yet. We have to either set up linear algebraic problems like we showed a few slides ago, or do Gauss-Seidel, also like we showed a few slides ago. Right? And so once I solve for this ti plus 1, I'm ready to move on to my next step. Right? So we're taking these sets of half steps, going one direction, then the other direction, then one direction, then the other direction, to treat both of our cases evenly and fairly. Right? This should give us a nice balance. Okay. Let's talk about some issues with our finite difference methods. So we've spent all of our time talking so far looking at finite differences. So the nice thing is that they're relatively simple to set up, right? So these finite differences, we can set up really easy if they're rectangular. The equations are simple to set up because I'm just plugging in i's minus 1s and substituting their cases, even if they are a little bit cumbersome to set up, but it's quite sort of straightforward. And we can divide the space finer and finer to refine these different methods. However, there are a few issues. The first being it requires a regular sized grid. So if I have something that's happening very fast, I need to have the same size grid. Maybe if this is happening fast, I need the same size grid as maybe some interactions that are happening that are slow, far away. So if I need to divide the grid over on the fast side, I have to divide the grid over on the slow side too. So this can be numerically challenging. Additionally, if I have complex things that are going to happen, so say a curve, it's also hard to implement, right? How do I take that curve into account? Not so straightforward, not so obvious. So what we need to do is have a different, more maybe complex method that we can have for complicated problems. So think about it like here on the right, where I have this insulated piece, and then I have this free convection piece over here. And then for this convection piece, because things are changing faster, I want to have a finer grid, right? Or maybe I want to have some sort of circular piece. Very, very difficult to do with finite differences. So what we're going to come up with is called a control volume, or the finite volume approach. So we're going to move away from having these nodes and calculating the point at each of these nodes, so point-wise definition, and instead make these sort of boxes around each node. And then, instead of saying, okay, we're going to have heat transfer or whatever between these two nodes, we're going to look at how much stuff goes into the box, how much stuff comes out of the box. And we're going to then say, we're going to want to assume at a steady state that these boxes, we're going to assume at steady state that what's going into the box and what's coming out of the box is equal, right? So whatever goes in has to come out. And then this is going to provide us a different way to set up our equations that are more versatile, including the ability to change box sizes. So everything doesn't need to be uniform, or change volume sizes. Change maybe what's happening here and what's happening here. There's different sets of equations that are going to control that behavior. It's going to give us more flexibility, but also be but also be a little bit more challenging. This is going to make up, constitute how many professional solvers of computational fluid mechanics or heat transfer reaction engineering operate. And because of this, there's entire classes dedicated to the subject. So today, I just want to give you a taste of how these methods work. And then if you're really interested in them, I recommend taking one of the many classes dedicated to this subject. Okay, so let's go through the concept. We've sort of touched on this concept, but let's go in a little bit deeper. So remember, in the finite volume approximation, we had these the finite difference approximation, we had these nodes that were separated by h. Now I'm going to draw this box evenly around each node. So it's still going to have length h, right? Because if I cut this in half and cut this in half, right, that would be h over 2, h over 2. So still this would give me a distance of h. And we're going to look at the flux entering that area h. And then we can look at the flux entering or leaving each of these individual pieces. So if we had an equation, say that was from a finite difference approximation that looks like partial squared t partial x squared plus partial t second partial t partial y squared equals 0, we need to backtrack and look and see where this is actually coming from, right? Because we need to look at the fluxes that are going in and out of the sides. And where this is really coming from is this heat balance, where we say the change in Q, so the change in heat in this cell with time, is the heat coming in minus the heat going out. And remembering that the heat in or out is the area times the heat flux. So there's that Q dot, and that heat flux is K dt. So we can write out each of these different pieces of what's going in and what's coming out. So what's coming in is from this right-hand side. So let's maybe write out Q in. Q flux in is K times d, maybe we'll call it Q in from the left, dt dx. So we're still going to use my definition of a derivative. So we're still going to say that dt dx is going to be temperature at point C, so that central point, minus what was happening to the left, minus TL over dx. Over h. So that's that distance, or we could write it over dx. Doesn't matter. Maybe better to put it over dx. Okay, so now I can calculate the Q, the total Q from the left. So that's the flux, which is K Tc minus TL over delta X times the area that it's moving through. So that's the height times the width. So maybe just we'll put in delta z, so whatever that width is into and out of the board. So that's my total QL. I can write this out for the heat leaving through the right-hand side. So Q out, right, is K times, now we need this derivative. So that's K times TR minus TC over delta X. So times my height times delta Z. And then we can look in the other two directions. So in the vertical direction, so we can say T in, so it's maybe coming from the bottom, from down, is going to be K dt dy times H times delta Z. So this would be K. So now if I'm coming in from the bottom, I need to look between these two pieces. So that's TC minus TD delta Y times H delta Z. And we have my last one from the top. So Q out top is K TU minus TC over delta Y H dZ. Right? And so I can take all of these pieces and write them out all together. We sum in all the ins, so dq dt is the ins, so that's ktc minus tl over delta x h dz plus ktc minus td over delta y h delta z minus what goes out, so that's k tr minus tc over delta x h delta z minus k tu minus tc over delta y h delta z. Okay, so now we've put all this together, and we want to find out what's happening here when without time effects, right? There's no time terms. We just set this equal to 0 at steady state. Now we have our governing equation for we have our governing equation for the finite volume method for this problem. Oops. So I can write this out. Write this out again. So this is our Q total. That's from that previous slide. It equals 0. There's my dt's going in and out the different pieces, and so we can solve this out again. So Q was we can simplify this. Remember, we can take each of those k's because they're in every single term. Cancel them out because they're 0. So we're left with excuse me, TC minus TL over dx minus TR minus TC over delta x plus TU d minus TC, oops, other way around, TC minus TD over delta y minus TU minus TC over delta y equals 0. And in this case, we say, if delta x is equal to delta y, we can rearrange all of these. We can get rid of all those bottom terms, and then we end up with TC. So there's 4 TCs minus TL minus TR minus TD minus Tu equals 0. So Tc equals 1/4 TL plus Tr plus Td plus Tu. Right? So this is exactly the same equation that we had when we did the finite difference approximation. Right? So no different. And it shouldn't be because we're addressing the same problem. And so if I have an evenly sized grid, it's much easier to use the finite difference method. But when I don't have a finite grid, an evenly spaced grid, or I want to have odd shapes like curves or triangles, we can't use that. So let's take another example that's a little bit more complicated, where we really would want to use the benefits of the finite volume method. So let's take this case. So here we have a blown up version of that initial picture. So we're going to have finite volume of this point that we're really interested in, situated here at this 4.2. And to the left of that 4.2 point, so over here, it's insulated. So that means there's nothing going in and out of the top. So remember, traditionally we would write that boundary condition as dt dy equals 0. In this case, because nothing's going in, we just don't add that term to our flux equations. We're going to have conduction coming in from the side. We're going to have conduction coming in from the bottom. Notice here how the height is only 1/2. This is because fully that node has another half sticking up on the top half, but that insulation is cutting it in half. So I really only have this area of h/2. I get that same h/2 on the bottom. Now, on the right-hand side of this equation, that top is open. And I'm going to have convection coming off the top. Because of that convection, I want to use a much finer grid. So in this case, this volume over here, this finite volume on this at this 4/3 point, only has an h/2 spacing. So when I cut it in half, I really only get h/4 for the finite volume that I'm interested in this equation. Okay, so let me clean this up just a little bit. So we're going to have a steady state heat flux again. So remember, this is going to say, dq dt equals 0. And then we're going to is the sum of those heat fluxes. Okay, cool. So we need to look at the different sides. So where all is heat moving in or heat coming out? So we can say, okay, heat's going to come in from the left side through conduction, and we're going to lose heat through the right side. So left side conduction positive, right side conduction negative. Now coming in from the bottom, we have conduction through this first material A, and then we're going to have heat coming in through this side through maybe material B. Right? And then we're going to lose heat up through the top. So that's why that subtraction is there due to convection. So now we need to tackle each of these individual pieces. So for conduction, we can say that Q equals K dt dx. And in this case, we can write out, just like we did before, what those individual Q pieces are. So for material A, we have Ka, and then we look at T4 minus T1. So we're taking that derivative over that space. Okay. So now we can look over the area. So now we need to get that full Q. So we need to look, how much area is this? Well, that's h/2, right? Because I've cut that piece in half. So we're moving in through this amount of area. Now we can look at convection. So what's happening at this piece, or we can write similar equations for the other pieces, but let's look at convection. In this case, my heat loss is H times TA, so that's what's up here, times my temperature here. So I can write this out. So there's my H of conduction, my T ambient, which is a variable, times that temperature T4. And in this case, this area is only H over 4. So that's the only area that I'm looking at. Okay, so we can start putting these pieces together. Whoops. We can start putting these pieces together. So here's my heat flux out the top. Here's my conduction. So we can write out these pieces. So let's tackle this left-hand side. So here we have Ka prime T24 minus T41. So what's the derivative here? Over H, because that's the distance between the two. Then this H over 2 is dealing with, because this is that height here. So now that's that side. So now we can look at the right-hand side conduction. Maybe I'll change color. Now we're going to look at conduction through this material, and we're going to take the derivative between these 2 points. So we have Kb, this case a different material, a different heat conductivity. I'm still taking that finite difference derivative between now 4, 2 and 4, 3. And then H over 2. So even though this distance is smaller, so this is H over 2, right? This distance was smaller than the 4, 1 to 4, 2, right? So that's why we have that H over 2. That area, that height through which the heat is flowing is the same size. So that's the right-hand side. I'm going to make a little bit of a note here. You might have noticed that these have sort of signs flipped from what we did in the early example. This is just a slightly different sign convention, but in the end, it leads to the same point, because I could multiply everything through by -1 and flip those signs. So now let's look at our lower conduction. So we're still going to move through material A, right? So this is A and this is material B. So we still have Ka, and now we need to see what's my derivative moving up. Okay, well, this is T42 minus T32. So that's that temperature difference here. So that's going to give me my dt dy term, essentially. So we have T42 minus T3, 2 over H, and we're moving through this area H2. Okay, so now we're ready for conduction on material B. So this side. So notice that now we have this Kb, because we're moving through material B again, but we still maintain the same derivative, right? These are the same, because that difference, that analytical or that numeric derivative is the same. It's still moving up from those 2 spots equivalently. Okay, so I have that same derivative piece, but now we have this H over 4, just because that volume we're saying is a smaller data set. Okay, and so then we're ready to do that final piece. So ready to do that final piece. Maybe we'll do dark blue. So that's the heat leaving out here. Now we plug in the equation for my convective piece, my HC. I have this piece, which is just given as this number. Notice we're going to use the temperature at 4.2, because that's the only temperature we've got. And once again, it's moving through only a slice that's H over 4. Okay, so we've set all of these equations up. We've set this equation up. We can now go through, set up equations, similar equations for all of these other nodes all these other nodes that are maybe sitting here. Here maybe is 3, 1, right? We can go in and we can write all these equations out for many more points and solve using Gauss-Seidel, or if it's linearizable, we could do turn it into a matrix and do matrix math. So let's make some final comments. So the finite volume method is useful because we can have many shape types. We could consider triangles, squares, many different types, and we can then differently shape those sizes so we can concentrate our computational effort in the regions where things are changing either fast, so having very small volumes, or slowly, and thereby having larger volumes. That way we can spend the computational resources where we need them. However, it's difficult because the equations that we need to build are not simple and are shape dependent, right? So we sort of just considered energy moving into and out of boxes. As I get to more complex shapes, so triangles, etc., or really more complicated shapes in 3 dimensions, the equations do get more challenging. So with that added flexibility and control, we have to pay a price, and that is in the complexity of building those equations. So let's review what we've done today. So we've covered, or in this chapter, in this content. So we've covered 2-dimensional finite differences. We've talked about time-dependent conditions, both explicitly and with implicit methods. We've talked about how we could implement Robin's boundary conditions. And then finally, today we talked about finite volume approaches, which once again are more complicated but give us more flexibility. If you really find this material interesting and are further interested, I highly recommend taking a class. Many of the programs that you are probably going to encounter, that you may encounter as engineers or in graduate school, are going to require solutions on these complex grids, whether they be in a finite difference approach or a finite volume approach. So it may give you a leg up to say, I already have experience with these types of methods. So with that, I hope you've learned a lot about an introduction to solving partial differential equations numerically, and I look forward to seeing you in class.